Light is only part of the story. There's another, more subtle language that the universe speaks. A language of ripples and echoes, written into the very fabric of space and time, revealing information about the objects and events that created these waves. Each detection tells a story of the formation and evolution of black holes, neutron stars, and even entire galaxies. The energy carried by gravitational waves does more than just stretch space. It allows us to map the universe's most extreme environments, to understand how black holes and neutron stars form, and to explore the very nature of space and time. Gravitational waves not only affect the space they move through, they also have profound effects on the very objects that create them. When two massive objects like black holes merge, the gravitational waves they emit carry away significant amounts of energy. This loss of energy directly impacts the motion and structure of the black holes themselves. When neutron stars collide, the effects are even more dramatic. Gravitational waves not only strip away energy, but also determine the final outcome of the collision. Whether a new, more massive neutron star is formed or whether the stars collapse into a black hole. These waves provide clues about the internal structure and composition of these dense, enigmatic objects. The gravitational waves we detect are signals from the heart of cosmic violence, revealing the forces at play, the incredible energies involved, and the final fate of these cosmic giants. They help us understand how stars live and die, how black holes are born, and how matter behaves in the most extreme environments imaginable. By combining data from detectors on different continents, we can determine the location of gravitational wave sources with much greater accuracy. When a gravitational wave passes through Earth, it arrives at each observatory at slightly different times. By measuring these time differences, we can pinpoint the source of the waves in the sky. The global network has enabled us to conduct multi-messenger astronomy, where gravitational waves are observed alongside light, radio waves, and gamma rays. Together, they paint a fuller picture of the most extreme cosmic events. Gravitational wave astronomy is truly a global effort. Scientists from every corner of the world are working together to unlock the universe's secrets, proving that in science, collaboration knows no borders. Gravitational waves come in a wide range of frequencies, each frequency revealing different stories about the universe. LIGO and its partner observatories are tuned to capture specific frequencies that align with some of the most energetic events in the cosmos. LIGO is designed to detect gravitational waves in the frequency range of approximately 10 Hz to 10,000 Hz. This range is well suited for capturing waves produced by events like the merging of stellar mass black holes or the collision of neutron stars. These frequencies fall within a range similar to that of human hearing, but instead of sound waves traveling through air, they are ripples traveling through space-time. Each gravitational wave signal can tell us about the objects that created it. For example, a merger of two black holes produces a chirp, a wave pattern that increases in frequency and amplitude as the black holes spiral closer together, culminating in a sudden peak as they merge. The unique signature of each chirp allows scientists to determine the masses, spins, and distances of the merging objects. However, not all gravitational waves fall within LIGO's detection range. Lower frequency waves, such as those produced by the mergers of supermassive black holes found in the centers of galaxies, lie outside LIGO's current capabilities. Detecting these lower frequency waves requires different types of instruments. This is where the future of gravitational wave astronomy comes into play. The planned Laser Interferometer Space Antenna, or LISA, will be positioned in space to detect these lower frequency gravitational waves. By expanding our observational range, LISA will allow us to hear those deep, slow rumblings of the supermassive black hole mergers and other cosmic phenomena, further extending our understanding of the universe. By broadening the range of detectable frequencies, we will open up new windows into the universe, enabling discoveries from the high-pitched chirps of merging neutron stars to the low-frequency growls of supermassive black holes colliding.
שאלנו בעלי עסקים איך B144 מקדמת את העסק שלהם, והתשובות היו מרימות.
איך שנרשמתי, פנו אליי כבר 4 פניות מאנשים שונים, ממקומות שונים בארץ, וכל יום פונה אליי לקוח אחר.
מעוררות את החושים.
B144, אני ממש מבסוט ממנה. באים אנשים קונים, וחשוב לציין שאנשים איכותיים.
עם ניחוחות של הצלחה.
ממש שירות נהדר, הרבה לקוחות מוצאים אותנו, אני כבר מוכן לעידן החדש של הדיגיטל.
ומה עם העסק שלכם? הצטרפו עכשיו לחבילת הפרסום בניהול המומחים של B144 ותקבלו יותר חשיפות ליותר לקוחות פוטנציאליים.
Each new frequency band brings with it new opportunities for understanding the cosmos. In August 2017, a groundbreaking moment in astronomy took place. For the first time in history, an astronomical event was observed in both gravitational waves and electromagnetic radiation. This event, known as GW 170817, marked the dawn of multi-messenger astronomy. GW 170817 was the merger of 2 neutron stars, the remnants of massive stars that had previously exploded as supernovae. As these neutron stars spiraled together, they emitted gravitational waves detected by LIGO and Virgo, and just 1.7 seconds later, NASA's Fermi Gamma Ray Space Telescope observed a burst of gamma rays pinpointing the event's location in the sky. This unique observation triggered an unprecedented global effort. Within hours, dozens of telescopes across the planet began observing the region in different wavelengths, from radio to X-rays, allowing scientists to study the event in detail like never before. The first ever joint observation provided critical insights into the universe's workings. It confirmed that neutron star mergers are key sites for producing heavy elements such as gold and platinum and scattering them throughout the cosmos. This was a long-suspected theory, now proven with direct evidence from gravitational waves. The discovery of GW 170817 demonstrated the immense power of combining gravitational waves and electromagnetic observations, allowing us to witness cosmic events with greater clarity and precision. It's opened a new window into the universe, where every detection tells a deeper and richer story. Multi-messenger astronomy represents a new era of discovery where light and gravitational waves together illuminate the most profound mysteries of the cosmos. Gravitational wave astronomy is still in its infancy, but its potential is vast. What could we uncover in the coming years and decades? What new mysteries of the cosmos might we solve? With more sensitive detectors and more powerful instruments, we might soon detect gravitational waves from sources we've never observed before. Could we hear the faint echoes of the Big Bang, confirming theories about the earliest moments of the universe? Detecting these primordial waves could provide direct evidence of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. It could answer questions about the fundamental forces that shape the cosmos. Gravitational wave astronomy could also reveal unknown phenomena, objects, or events that we've never imagined. Exotic forms of matter, hidden dimensions, or the mysterious dark matter that makes up most of the universe's mass. Gravitational waves could help uncover these elusive secrets. We are standing at the edge of discovery, poised to answer some of the most profound questions ever asked about our universe. Gravitational wave astronomy offers a new way to explore the cosmos, opening a path to discoveries beyond our wildest dreams. The universe is full of whispers, and we are just beginning to listen. There is a phenomenon in the field of astronomy that has intrigued and puzzled scientists for years. Hidden behind the glittering veil of the Milky Way, in the region of space we call the avoidance zone, there exists a gravitational anomaly so vast, so powerful, that it tugs at the very fabric of our universe. This is the Great Attractor. Although invisible to our telescopes, its gravitational influence is so great that it affects the motion of galaxies hundreds of millions of light years away, including our own Milky Way. But what is the Great Attractor? Is it a supermassive black hole? A colossally dense cluster of galaxies? Or something else entirely? And more importantly, what does its existence mean for us, for our galaxy, and for the future of the universe?
אנשים עם עסקים, זה בשבילכם.
לבקש מלקוח לבצע העברה בנקאית. איפה זה פוגש אותי? בעיקר כאב ראש. זה עונש בשבילי ובשביל הלקוח. זה מלא פרטים קטנים ובעיקר מסורבל.
אנשים עם עסקים, אמצעי תשלום חדש רק בגרו. לראשונה בישראל, אפשר לקבל תשלום על שירותים ומוצרים בהעברה בנקאית. בקלות, בלי התעסקות ועל הדרך לחסוך בעלויות. גרו, בנקאות חדשה לאנשים עם עסקים.
In this video, we'll explore these questions, delving into the impact of the Great Attractor on our galaxy and the challenges scientists face in observing this elusive region of the cosmos. We'll also travel to the recently discovered South Pole Wall, a vast cluster of galaxies stretching at least 700 million light years into space, and its intriguing connection to the Great Attractor. So, will we eventually be consumed by this anomaly, or does it still serve another purpose in the grand scheme of the universe? Let's find out. About 4 decades ago, astronomers used the Parkes telescope to peer through the dust of the Milky Way. They discovered that our galaxy is traveling through space much faster than expected. Imagine, our Milky Way is traveling through space at 2,500 times the cruising speed of an airliner, 55 times the escape velocity of the Earth, and even twice the escape velocity of the galaxy itself. But where does such movement come from? Here's the mystery. The theory of our origin, based on the Big Bang, tells us that every point in the universe should fly apart from every other point. However, the galaxies on either side of us should be moving at the same recessional velocity, which should not result in net motion in the Milky Way reference frame. Net motion can arise from nearby clusters in the distribution of matter, such as a massive cluster of galaxies. The additional gravitational attraction of such a cluster of galaxies can slow down and even reverse the expansion of the universe in its immediate vicinity. But in the direction of motion of the Milky Way, such a cluster is not obvious. There is an excess of galaxies in the general vicinity and an excess of radiation visible in X-ray telescopes, but nothing that somehow seems large enough to explain the results. So what are we observing? A super density of pure dark matter? Or is the current theory of the origin of mass and motion wrong? Astronomer Alan Dressler of the Carnegie Institution used the first explanation, dashingly calling the missing concentration of matter the Great Attractor. But the mystery of the Great Attractor continues to baffle us. Despite our best efforts and the discovery of new galaxies, galaxy clusters, and new threads in the cosmic web, we still haven't found enough to explain our motion. The Great Attractor remains a mystery, pulling in our Milky Way and leaving us with more questions than answers. So over a vast expanse of space, some 220 million light years away, there is a gravitational anomaly known as the Great Attractor. This region of space, located within the Laniakea supergroup, has such an enormous gravitational pull that it affects the motion of galaxies for hundreds of millions of light years, including our own Milky Way. But what is a great attractor? The term great attractor was coined to describe its gravitational influence, but it is not actually a single entity, but rather a region of space with a higher concentration of mass. This mass consists not only of visible matter like stars and galaxies, but also dark matter, an invisible and mysterious form of matter that by some estimates makes up about 85% of the mass of the universe. Understanding the Great Attractor is like putting together a cosmic puzzle. We know it's there because we can observe its gravitational effects, but we cannot see it directly because it's located in the avoidance zone, a region of space hidden by the dust and stars of the Milky Way. Despite these challenges, scientists have made significant progress in studying the Great Attractor. They have used various techniques, such as X-ray, infrared, and radio observations to peer through the dust and gas of the Milky Way and gain insight into this mysterious region of space. According to information to date, the Great Attractor is part of a larger structure called the Norma Cluster, which is one of the most saturated known galaxy clusters. It is in this cluster that the center of the Great Attractor is located. The Norma Cluster is moving toward the Great Attractor at an astounding speed of about 1,340 miles per second. So as we've said, the gravitational influence of the Great Attractor. As research continues, our understanding of the universe is being challenged. Theorists are beginning to question the validity of the space-time metric we currently use to describe the universe. There's even talk of changing the general theory of relativity on large scales. As we look out into the cosmic expanse, we can't help but ponder the future of our universe. What does the accelerated expansion of the universe due to dark energy mean for us, for the Milky Way, for our Great Attractor, for the countless galaxies dotting the cosmic landscape? The universe is not static. It is expanding, and this expansion is accelerated by a mysterious force called dark energy. This force is so powerful it stretches the very fabric of space-time, causing galaxies to diverge from each other. But what does this mean for the future of galaxies and superscales? And what role does the Great Attractor play in this cosmic drama? Despite the expansion of the universe, the Great Attractor continues to exert gravitational influence on the galaxies surrounding it, including our Milky Way. So back to the burning question, will the Great Attractor swallow us up? The answer is no. Despite its enormous gravitational pull, the Great Attractor is not a cosmic monster ready to swallow us whole. As the universe expands, its gravitational influence will weaken.
תודה. תודה רבה. יאללה, מחר? מחר. לא, מחר יש לי פרוצדורה בברך. נכון, אנחנו נבוא לבקר אותך. ברור שנבוא. יו, איזה חמודות, זה באר שבע, כן? אין לך אותו מחר. נכון. וגם, יש לנו את זה. עם ההוא, נכון. חבל שאת לא במכבי. את יכולה לבחור שם באיזה בית חולים לעשות את הניתוח. ממש חבל. מה את משחקת אותה? גם את לא במכבי. לא משנה, אני אלך לבד.
אל תהיו מקופחים, רק חברי מכבי יכולים לבחור מתוך הכי הרבה בתי חולים.
סתם עושה.
ברור, מכבי, בריאות זה הכל.
The distant future, as the expansion of the universe continues to accelerate, galaxies that are currently attracted to the Great Attractor may begin to move away. The gravitational bonds holding the superclusters together will weaken, and these massive structures may begin to disintegrate. The future of the universe is a vast, ever-expanding cosmic sea with galaxies like islands drifting in the cosmic ocean, slowly moving away from each other. The great attractor, once a formidable gravitational anchor, will eventually lose its power over the galaxies around it. In the vast expanse of our solar system, among the swirling gas giants and rocky Earth-like planets, an intriguing world lurks, a world larger than the planet Mercury, but orbiting not around the Sun, but around the colossal planet Jupiter. This is Ganymede, the largest satellite in our solar system. Ganymede, covered in a thick, icy shell, has attracted scientists for years. Its battered and scarred surface tells a story that's been billions of years in the making, a story we're only beginning to unravel. Beneath its icy exterior, Ganymede hides secrets that could forever change our view of life in the universe. It's currently the only known moon that has its own magnetic field, and deep beneath its surface, there may be more water than all of the Earth's oceans combined. Today we take a trip to this distant moon. We'll study its recent images and delve into the mysteries these images have begun to reveal. Our story began more than 4 centuries ago in 1610, when a man named Galileo Galilei pointed his primitive telescope at the night sky. He discovered 4 points of light orbiting the giant planet Jupiter that forever changed our view of the universe. These were Galileo's satellites, and the largest among them was Ganymede. Galileo's observations of these Galilean moons revolutionized our understanding of the cosmos by providing the first evidence that not all celestial bodies revolve around the Earth. Ganymede is the titan among the satellites. Its diameter is about 3,273 miles. It is the largest moon in our solar system, surpassing even the planet Mercury in size. But size isn't the only thing that sets Ganymede apart. Transported to present day, our ability to study Ganymede has kept pace with technological advances. Modern telescopes, both ground-based and space-based, have given us a clearer picture of this distant moon. But it was the advent of space probes that really ushered in a new era of exploration. Spacecraft such as the Galileo Orbiter and the Juno probe have traveled to the Jupiter system to send back to Earth detailed images and data that have allowed us to study Ganymede like never before. These missions have given us a close-up view of Ganymede's surface, revealing its icy terrain and the intriguing patterns etched on it. Ganymede is a moon of contrast. Its surface is a patchwork of 2 different types of terrain. Darker areas filled with craters and grooves tell of the moon's turbulent past, while lighter areas hint at dynamic and geologically active world. An equally tantalizing aspect of Ganymede lies beneath its icy surface. Scientists believe there is a vast ocean of liquid water beneath the ice, containing more water than all of the Earth's oceans combined. Zeus, known as Jupiter in Roman mythology, took a beautiful mortal boy to become the cupbearer of the gods. This boy's name was Ganymede. It seems appropriate that the moon carries such a large amount of water around Jupiter. But perhaps the most intriguing feature of Ganymede is something we can't see. It's the only moon in our solar system that generates its own magnetic field, a trait usually reserved for planets. This magnetic field creates beautiful auroras in Ganymede's rarefied atmosphere, a sight truly worth seeing. The question arises, could this distant, icy world harbor the conditions necessary for life? Our understanding of Ganymede has been greatly enhanced by the daring missions sent to the Jupiter system. One of the most significant of these was the Galileo mission launched by NASA in 1989. Galileo arrived at Jupiter in 1995, embarking on a nearly 8-year mission to study the gas giant and its satellites. The spacecraft made several close flybys of Ganymede, taking detailed pictures of its icy surface and measuring its magnetic field. The data collected by Galileo revolutionized our understanding of Ganymede, revealing its complex geological history and confirming its magnetic field. This feature distinguishes it not only from other satellites, but also from most planets. Ganymede is the only satellite in our solar system that generates its own magnetic field. The magnetic field is created by the movement of molten iron in the core of the celestial body, a process similar to that which generates the Earth's magnetic field. However, the main mystery is that judging by the structure of the satellite and its age, the core of Ganymede long ago should have cooled and solidified. But still, how does the Moon create a magnetic field? The answer may lie in a process called tidal heating. As Ganymede orbits Jupiter, the planet's gravitational pull causes the Moon's interior to contract and stretch. To understand tidal heating, let's think about a simple everyday activity: kneading dough. When you knead bread or pizza dough, you're exerting force on it, pushing and pulling in different directions. As you work with the dough, you may notice that it begins to heat up. This is because the force you are applying creates friction within the dough, and friction generates heat. That's very similar to how tidal heating works. In the case of Ganymede, the kneading is done by Jupiter's gravitational pull. As Ganymede rotates around Jupiter, the planet's gravity attracts different parts of the Moon with different forces, causing it to bend and stretch. This bending and stretching creates friction within Ganymede, and as with dough, the friction generates heat. This heat could be enough to melt part of Ganymede's interior, creating a layer of liquid metal that would generate the Moon's magnetic field. Among other things, Ganymede's magnetic field is unique in that, unlike Earth's, it's embedded in Jupiter's powerful magnetosphere, creating a complex and dynamic electromagnetic environment. This magnetic field is important for the potential habitability of Ganymede. It creates a magnetosphere around Ganymede that could theoretically protect life on the Moon from harmful solar radiation. In addition, the interaction between Ganymede's magnetic field and Jupiter's magnetosphere produces auroras in Ganymede's thin atmosphere. These auroras have provided scientists with valuable information about the internal structure of Ganymede, for example, confirming the presence of an ocean beneath its surface. More recently, the Juno spacecraft has been studying Jupiter and its satellites. Launched in 2011, Juno's primary mission is to study Jupiter's composition, its gravitational field, magnetic field, and polar magnetosphere. In June 2021, NASA's Juno spacecraft made a close flyby of Ganymede, coming within 645 miles of the Moon's surface, taking the most detailed images of the Moon's surface to date. The spacecraft's JunoCam imaging system had only 25 minutes to take images of Ganymede, but in that short time, it managed to take 5 stunning exposures. Interesting fact: initially, during development, Juno was not equipped with a camera. It was project manager Scott Bolton who insisted, "We've got to put a camera on this thing," and it was indeed a wise decision. These images show Ganymede's complex and intriguing surface, with a mix of darker areas and strong craters and lighter areas and grooves and patterns. The Juno science team is now comparing these images with those from previous missions, looking for any changes that may have occurred over the past 2 decades. But taking these pictures wasn't easy. Juno had to rush past Ganymede at 12 miles per second and then glide over the tops of Jupiter's clouds at 36 miles per second. Nevertheless, despite these challenges, the spacecraft managed to take clear and detailed images of Ganymede, giving us an unprecedented view of this fascinating moon. These images are not only visually stunning, but they're also key to understanding Ganymede's geology and the potential for life. For example, the images show light and dark areas on Ganymede's ice shell, indicating differences in the purity and composition of the ice. This information can help scientists understand how Ganymede's ice shell formed and how it's changed over time. So let's take a closer look at the dynamic geologic history of this moon. The dark regions are considered the oldest parts of Ganymede's surface, some 4 billion years old. They are heavily cratered, indicating they have been relatively stable for a long period, bearing the scars of countless impacts. In contrast, the lighter colored groove regions are younger and indicate more recent geologic activity. These regions are mottled with intricate patterns of ridges and ditches, some of them more than a mile high and hundreds of miles long. These furrowed landforms are thought to have formed as a result of tectonic activity caused by the previously mentioned tidal heating from Ganymede's elliptical orbit around Jupiter. When the moon bends and stretches under Jupiter's gravitational pull, it releases heat that can cause the icy surface to crack and regenerate. This process can create faults and cracks in the surface, resulting in the ridges and grooves we see today. It is a process similar to plate tectonics on Earth, but in a much colder and alien environment. Thus, by studying these geologic features, we not only learn about Ganymede's past, we also gain insight into geologic processes that may occur on other icy moons and planets, helping us to understand the diversity of worlds in our solar system and beyond. As we delve deeper into the mysteries of Ganymede, one question arises: could this icy moon harbor life? While we don't yet have definitive answers, some features of Ganymede make this a tantalizing assumption. First, it's believed that Ganymede has an underground ocean of liquid water more than 100 kilometers deep. This ocean is warmed by heat generated with tidal bends. On Earth, wherever we find water, we find life. So the presence of a vast ocean on Ganymede opens up the possibility of life there, perhaps in an environment similar to Earth's deep-sea hydrothermal vents. These vents, spewing mineral-rich water heated by the Earth's interior, are teeming with life forms that thrive in extreme conditions. Could similar vents exist on Ganymede, providing the conditions necessary for life? Second, Ganymede's thin oxygen atmosphere, although not suitable for human respiration due to the low density, could potentially support some forms of microbial life. On Earth, some microbes are known to survive in extremely rarefied atmospheres, such as those at high altitudes of mountains. Although conditions on Ganymede are harsh and very different from those on Earth, life as we know it has proven to be incredibly adaptable and able to survive in a wide variety of environments. Thus, the possibility of life on Ganymede, while somewhat speculative, cannot be ruled out. As future missions explore this fascinating satellite in more detail, we may yet find answers to these questions. Who knows what secrets Ganymede may reveal? However, it's very important to be aware of the challenges and limitations of exploring such a distant and alien world. First, the sheer distance. Ganymede orbits Jupiter, which is about 484 million miles from Earth. Even traveling at the speed of light, it takes more than 40 minutes for a signal to travel from Earth to Ganymede and back. This makes real-time control of spacecraft impossible and means that missions to Ganymede must be able to operate autonomously for long periods. In addition, the harsh conditions of Ganymede itself make themselves felt. The surface temperature of negative 276 degrees Fahrenheit, and it's exposed to intense radiation from Jupiter's magnetosphere. Any spacecraft that visits Ganymede must be designed to withstand these extreme conditions. And finally, there's the problem of interpreting the data we're getting. Images and other data from Ganymede must be transmitted hundreds of millions of miles through space and then analyzed by scientists on Earth. This process requires sophisticated technology and expertise, and there's always some degree of inaccuracy involved. It's not to say that current interpretations are wrong, but rather our understanding of Ganymede is constantly evolving as new data is collected and analyzed. Although the scientific community seems to be in general agreement on the main features of Ganymede, there's also some uncertainties. One major point of contention is the source and nature of the plumes observed on Ganymede's surface. Some scientists believe these plumes are caused by water from the interior of the moon being pushed through its icy crust, similar to the plumes observed on Saturn's satellite Enceladus and possibly Jupiter's satellite Europa. Incidentally, we've already debated whether there is life on Europa in another video. Similarly, While the existence of subsurface ocean on Ganymede is supported by several lines of evidence, the exact properties of this ocean, such as depth, composition, ability to harbor life, all still the subject of ongoing research and debate. Despite these challenges, our quest to explore Ganymede and other distant worlds continue. Each challenge we overcome brings us one step closer to understanding our place in the universe. As we traveled through the mysteries of Ganymede, it became apparent that our exploration of this fascinating satellite is far from over. NASA and other space agencies around the world have ambitious plans to explore the Jupiter system. The European Space Agency's JUICE, their mission launched April 14, 2023, from the Guiana Space Center on an Ariane 5 launch vehicle, and it will make detailed observations of Ganymede and other Galilean moons, Europa and Callisto. The Jupiter Icy Moons Explorer will be equipped with a suite of 10 advanced instruments capable of studying the surface and interior of Ganymede with unprecedented precision. It'll map the moon's icy envelope and underlying ocean, study the composition of its surface and atmosphere, and further explore its unique magnetic field. Beyond JUICE, there are proposals for even more ambitious missions. These include landers, rovers, and even submarines to explore Ganymede's ocean. While still in the conceptual stage, these missions represent the bold, innovative thinking that will be required to fully unlock the secrets of Ganymede. As we look to the future, one thing is clear. Ganymede remains a tempting place for scientific exploration. Its unique geology, magnetic field, and potential for life make it a solid target in the ongoing quest to understand the workings of the solar system and our place in it. The speed of light is one of the most fascinating and mysterious concepts in the universe. It's considered the cosmic speed limit, beyond which nothing can move faster. However, what if I told you that it's possible to reach this incredible speed? While it may seem impossible, the laws of physics make it possible. In this video, we'll explore the fascinating world of the speed of light and how you can get closer to this incredible speed. So fasten your seatbelts and get ready for a journey into the unknown as we explore the limits of what's possible in the universe. First, let's recall what speed is and how light works. So in physics, we call speed a certain value equal to the distance an object travels in a certain time without an exact direction. When an object moves, it increases its mass and the level of its kinetic energy. So the faster it moves, the more mass it will gain and its energy will increase. Therefore, for example, the faster a space rocket moves, the greater the scale of destruction if it collides with a meteorite body, and the more energy will be consumed. In particular, objects can change their speed depending on the medium and its molecular composition due to friction. So this all works for objects that have mass. But what about particles that have no mass, like photons? Let's turn now to what we know about light. Light is an electromagnetic wave resulting from the emission of energy from heated bodies that are perceived by our eyes. However, light is probably also a wave and can be described as a stream of massless particles or quanta photons. Light has a speed of 186,000 miles per hour, and in a cosmic vacuum, it's the likely speed limit for the entire universe. This is what Albert Einstein's fundamental work, which changed the way we understand our universe, tells us: general relativity. If we summarize this theory in one sentence, its main idea is that gravity is a curvature of space, not a force that acts on all objects, and the laws of physics apply equally everywhere. But what does this have to do with light? According to GR, light is constant. That is, it always has the same speed and is probably the fastest phenomenon of all. The reasons for this are the absence of mass of photons and the absence of light moving along the timeline. According to GR and the parabolic model of Hermann Minkowski, Einstein's teacher, time is unified, meaning that there are no separate time and space. Our universe has 4 dimensions, 3 spatial, x, y, and z, and a temporal, t, dimension. Since space is one, everything in it is interconnected. Therefore, depending on your location in space-time, you interact with time and space differently. Let's imagine this using a simple coordinate system with a time and space line. If you're sitting here watching this video, for example, you are moving only in time. Your position in space does not change and you have no speed at all. However, if you decide to go to the store, then you'll be moving in both time and space. It's precisely because of the fabric of space-time we cannot synchronize watches because of the time dilation. This was also proven by scientists in 1971. The researchers placed hydrogen clocks in airplanes on the ground and flew around the world. After landing, it turned out the clocks on the airplanes were running slower by about 1/1,000,000th of a second. Light, on the other hand, moves only in space. It does not feel the influence of time, so if we were to put a clock on it, it would seem to be suspended. Moreover, since light has no mass, it's not affected by gravity. However, if it passes near a black hole or a star, or more precisely along the geodesic lines of space-time near a massive body, its path and energy consumption increase and curve, but its speed remains constant. So if the speed of light is constant and photons are not affected by time, especially in space, how can we achieve or even surpass it? An object with mass, like you and me or a spacecraft, cannot move at the speed of light because it would require infinite energy. However, interestingly, there is another reason. We are already moving at the speed of light. We learned this from Minkowski's model. The faster we move, the slower our clocks go. However, since we have mass, time affects us and we're not physically moving at the speed of light. Our speed is scattered between time and space. Even charged particles cannot reach the speed of light because they also have mass. Scientists are trying to accelerate subatomic particles to the constant of light using linear accelerators with the help of an electromagnetic field, but their speed is always 99.99%. However, at the end of the 20th century, scientists discovered a strange phenomenon, namely the so-called FTL, the movement of particles several times faster than photons. Thus, while observing the galaxy M87 and its jet, a beam of ionized matter ejected from galaxies at high speed. A group of researchers took several pictures of the jet. They noticed that the jet seemed to be moving faster than light. However, this is probably just an optical illusion caused by photons that were emitted later from almost the end of the jet. So it seems to us the light from it travels a shorter distance. Moreover, there's another phenomenon in space that can accelerate particles to the speed of light, but this time it is true: magnetic explosions. When magnetic fields collide with each other, they can often become entangled. If the tension between them increases greatly, they will break apart, which will throw all the charged particles away in an ultra-high speed. This process can be considered a natural particle accelerator. However, this is all about measurements in a vacuum. Recall that light travels through a certain medium, such as water, more slowly than in a vacuum. So charged particles can move faster than light, but in some kind of medium. The proof of such FTL motion is Cherinkov's irradiation. When a particle moves faster than light in some medium, it polarizes other particles, or in other words, it repels or attracts. When the charged particle moves further, the electrons are returned, which causes the butte glow of the irradiation. One hypothetical subatomic particle could be another competitor to light in speed. In 1962, scientists considered the possibility of the existence of particles that would be faster than light with the inclusion of GR. But in their work, they noted that such particles could move faster than light from the moment of their appearance and not by increasing their speed, which is not contrary to GR. These theoretical particles were called tachyons. Unlike other particles, a tachyon has energy, but its mass at rest is imaginary, meaning it has a mass only when moving faster than light. It's also likely that an approaching tachyon will be invisible because light travels slower than it. In particular, it's also hypothesized to speed up when it loses energy. It's believed that a tachyon is formed when energetically strong cosmic rays hit the Earth's atmosphere. So far, the existence of tachyons has not been confirmed, and therefore light can be considered the speed limit at the moment. In addition, tachyons can lead to logical temporal paradoxes. For multiple observers, a tachyon can travel to the future and the past. So, if a tachyon can travel back in time, this leads to the classic causal paradox, for example, in which a traveler can affect his own existence and prevent his own birth or send a message to himself in the past. However, does superfast motion really lead to traveling back in time? In fact, faster-than-light travel is not necessarily the cause of paradoxes. For one observer, a spacecraft whose speed exceeds the light constant will travel back in time, so it will also land in the past before it took off. However, according to the physicist Sabine Hassenfelder, such paradoxes are possible from the standpoint of special relativity, not GR. Thus, another observer, for example, can move along with matter in the same direction, forward in time, which means that the ship for him moves only forward, and therefore cannot break the causal relationship and first land and then only take off. In fact, the second observer follows the entire process, and therefore does not see any logical violations that arise from the perspective of the first observer, who believes that the ship is moving backward. So we can't simply accelerate to the speed of light. However, we know that light travels in space-time. What if we could bend space so that light travels a longer way than the object around which space is deformed? It sounds fantastic, but scientists are considering this space travel option. This concept is called the Alcubierre drive or warp drive. The idea of a warp drive is to stretch the canvas of space into a wave which should hypothetically compress the space in front of an object, such as a ship, and expand the space behind it. Thus, the ship will essentially move on this wave in a so-called warp bubble faster than light. Alcubierre's drive consists of three parts: the inner bubble or passenger space, where time passes more slowly than in the general space, and two outer parts, a shell of negative and positive energy and normal space without changes. However, warp drive requires a conceptual negative energy, which is impossible according to GR, but can exist in quantum theory in small quantities. This is one of the main problems of this theory. So to be able to implement it, it is desirable to find a method using positive energy. In 2021, astrophysicist Eric Lentz was able to develop such a concept. According to his model, such a bubble should contain a liquid plasma with a huge mass, about 10% of solar energy, and electromagnetic fields that would be located around the ship in the shape of diamonds. Such a bubble would be able to transport the ship, but only at a speed close to the constant of light, meaning that such a drive would not be able to accelerate to FTL. So far, it's impossible to confirm whether warp drive can exist without negative energy, as well as to start experimental work on it in general. However, if warp drive can work without the use of negative energy, then in the future, we'll be able to travel to distant planets much faster than with current technology. Another way that negative energy could hypothetically allow us to travel in time actually faster than light is through Einstein-Rosen bridges or wormholes. Einstein first came up with the idea of the existence of such tunnels from one place in space to another. It's believed that wormholes can be connected at gigantic distances of several million light years. However, although they have not yet been found, wormholes are very unstable, so they can quickly disappear due to negative energy. In addition, they're probably not as wide as we imagine. Also, because of this energy, wormholes must be small for a person to pass through. Therefore, until scientists find a way to keep both wormholes stable and large enough to confirm their existence, we cannot use this method for travel. Finally, quantum physics offers an interesting hypothetical way to transmit information at speeds greater than the light constant. This method of FTL communication is called quantum entanglement. In fact, quantum entanglement is an inseparable combination of two quanta that can exchange information with each other faster than light, despite the distance. Particles communicate by changing their state, for example, by changing their spin or energy. So during a long-distance travel in space, hypothetically, an astronaut could send a signal about possible life on the exoplanet under study, and this signal would reach the controller almost instantly. However, in reality, it is their variability and randomness that's the main problem that makes this concept of FTL information exchange unlikely. Quanta cannot be brought into a certain state to transmit any data because then the particles will break the connection with each other, and the particle whose state has not changed would show random results. So communication in this way would be impossible and probably not even reach the speed of light, because information cannot be transmitted at a speed greater than the light constant according to quantum mechanics. Moving at the speed of light or even faster gives us a serious advantage in space exploration. At the moment, we're not able to achieve this speed, but the hypothetical ideas of warp drive and tachyons, as well as the use of knowledge about FTL in different environments, can be an important step towards further research into ways to achieve the light constant. However, this is still in the distant future, so our priority now is to develop the technical knowledge we have so that our main goal in the study of space-time will be speed. In the vast expanse of space, among the countless stars twinkling in the night sky, celestial events of unimaginable scale and power take place. Events that eclipse entire galaxies and reverberate throughout the universe. Today we will delve into one such event, the stellar cataclysm known as a supernova. From ancient civilizations that saw these events as omens to modern astronomers studying them to understand the universe, supernovae have always fascinated us. Recently, the star Betelgeuse has dimmed dramatically, leading some scientists to speculate that it may soon turn into a supernova. If it does, it would be the brightest supernova observed from Earth in more than 400 years. Today we're going on a journey to understand these stellar cataclysms and their impact on our planet and their story of our place in the cosmos. We dive into the fascinating world of supernovae. In the great theater of the cosmos, the stars are the protagonist. They are born, they live, and they die. But some stars give such a spectacular performance in their final act that it outshines entire galaxies. They are supernovae, the catastrophic death of stars. But what is a supernova? Simply put, a supernova is a powerful and bright stellar explosion. It occurs during the last stages of a star's life, when the nuclear fusion in its core can no longer support the outer layers of the star. This causes the nucleus to collapse under its own gravity, leading to a violent explosion that can briefly obscure the entire galaxy. The energy released by a supernova is so enormous, it's equivalent to the energy that our sun would radiate over its entire 10 billion year lifetime. Supernovae are not just fascinating cosmic phenomena. They play a crucial role in shaping the universe. They are responsible for the distribution of elements throughout space, elements necessary for the formation of planets and life as we know it. In fact, it's believed that most elements heavier than iron, including gold and platinum, were formed by supernova explosions. So the gold in your jewelry, the iron in your blood, the calcium in your bones, all of these were once part of a star that was cut short by a spectacular explosion. Long before telescopes, space probes, and modern astronomy, ancient civilizations were already observing the stars. They noticed patterns, mapped constellations, and recorded celestial events. Among these events were the sudden appearances of new stars, which we now know as supernovae. One of the earliest recorded observations of a supernova was made by Chinese astronomers in 185 AD. They described a guest star that appeared in the sky, was visible in daylight for several weeks, and disappeared after about 8 months. We now know it was a supernova, and its remnants, known as RCW-86, have been observed with modern telescopes. Another famous historical supernova is SN 1054, Crab Nebula, discovered by Chinese and Arab astronomers in 1054. This guest star was about 4 times brighter than Venus and was visible during the day for 23 days. The remnants of this supernova are what we now call the Crab Nebula. The ancient observations of supernovae had a profound effect on the way these civilizations understood the cosmos. They challenged the idea of an unchanging universe, an idea prevalent in many cultures. They were also used for astrological predictions and were often seen as omens. Today we continue to study supernovae not as omens but as opportunity to learn more about the life cycle of stars, the creation of the elements, and the history of our universe. Although our understanding of the cosmos has grown, these stellar explosions continue to fascinate us with their power and mystery. Recently, the star Betelgeuse in the constellation Orion has attracted the attention of astronomers. Betelgeuse, a red supergiant, is nearing the end of its life, and at the end of 2019 it began to dim dramatically, leading some to speculate it may soon become a supernova. However, it has since returned to its normal brightness. The most widely accepted explanation for this event is that the star emitted a large dust cloud, which obscured some of its light and made it dimmer from our perspective on Earth. When the dust cloud dispersed, Betelgeuse's brightness returned to normal. This serves to remind us the universe is not a static place, but a place where stars are born, live, and die in spectacular ways. Every star in the night sky has a story to tell, a story that begins long before we see its light. The life cycle of a star is a journey of transformation, from a mere cloud of gas and dust to a beacon of light that can outshine a galaxy. The journey begins in nebula, a huge cloud of gas and dust. Inside these cosmic nurseries, pockets of gas and dust begin to collapse under their own gravity. When they collapse, they heat up and form a protostar. Over millions of years, the protostar continues to gather mass from the surrounding nebula. As it grows, the pressure and temperatures in its core increase. When the core temperature reaches about 27 million degrees Fahrenheit, nuclear fusion begins. The protostar is now a main sequence star, just like our Sun. A star can remain on the main sequence burning hydrogen in its core for billions of years, but eventually the hydrogen fuel runs out. What happens next depends on the star's mass. In stars the size of our Sun, the core shrinks and heats up, causing the outer layer to expand. The star becomes a red giant. Eventually, the core collapses and the outer layers are ejected, forming a planetary nebula. This leaves a white dwarf. But as we travel through space, we find that not all stars meet their end in the same way. A star can also go supernova. Its type will largely be determined by the mass and composition of the original star, while also having its own unique characteristics. For example, spectral analysis of Type 1 supernovae lack hydrogen lines. The most famous subtype, Type Ia, occurs in a binary stellar system. A white dwarf, the dense remnant of a star similar to our Sun, sucks matter from its companion star. Once the white dwarf reaches a critical mass, it undergoes a thermonuclear explosion, resulting in a supernova. On the other hand, type IB and IC supernovae are thought to result from the collapse of the cores of massive stars that have lost their outer layers of helium, and for type IC, helium. Now, let's focus on one of the most common types of supernovae we observe, type 2. These supernovae originate from the massive stars much larger than our own sun. Stars with at least 8 times the mass of the sun can undergo this dramatic transformation. Throughout their lives, these massive stars are in a constant battle between gravity pulling inward and the force of fusion pushing outward. When a star exhausts its nuclear fuel, gravity wins the battle. The core of the star collapses under its enormous gravity. This collapse of the nucleus occurs incredibly quickly, in just a fraction of a second, and leads to a powerful explosion, a supernova. The outer layers of the star explode in a spectacular spectacle, outshining the entire galaxy for a short time. What's left of the star may form a dense neutron star, or if it was massive enough, a black hole. But the legacy of the star lives on. The explosion disperses the elements formed during the life of the star into space, seeding the cosmos with building blocks for new stars, planets, and even life. When a star goes supernova, it's not just a spectacle of light. It's one of the most energetic events in the universe. The amount of energy released in a supernova explosion is so enormous, it's equivalent to the energy the sun would radiate over its entire 10 billion year lifetime. But where does all this energy go? Most of it is carried away by neutrinos. These tiny, nearly massless particles are produced in huge quantity during a supernova. They travel at nearly the speed of light, taking about 99% of the explosion's energy with them. The rest of the energy is released as light and other forms of electromagnetic radiation. This includes gamma rays, the most energetic form of light, and X-rays, which are less energetic but still much more powerful than the light we see. The visible light from a supernova is so bright that it can briefly obscure the entire galaxy. This light can be seen at great distances, making supernovae important cosmic beacons for astronomers. Although supernovae are interesting to observe, they can also pose a potential danger. The enormous energy and radiation released in a supernova explosion can have significant consequences, especially if the supernova is close enough to Earth. One of the main causes of concern is the impact on our planet's ozone layer. The ozone layer acts like the Earth's sunscreen, protecting life from the sun's harmful ultraviolet radiation. But an intense gamma-ray burst from a nearby supernova could destroy the ozone layer, increasing the amount of UV radiation that reaches the Earth's surface. This increased UV radiation can have harmful effects on the Earth's biosphere. It can lead to higher rates of skin cancer in humans and other animals, and disrupt photosynthesis in plants, potentially affecting the entire ecosystem. In addition to gamma rays, the supernova also emits a stream of high-energy cosmic rays. These particles can further damage the ozone layer as well as create streams of secondary particles in the Earth's atmosphere that would increase the radiation dose. In our study of the dangers posed by supernovae, there's another interesting aspect to consider: gravitational waves. These are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Albert Einstein predicted the existence of gravitational waves in 1916 in his general theory of relativity. Einstein's mathematics showed that the massive accelerating objects like a neutron star or a black hole orbiting each other would collapse space-time in such a way that distorted space waves would emanate from the source. And supernovae, with their incredible mass and explosive energy, are the first candidates to create such waves. When a massive star collapses and explodes, the asymmetry of the explosion can potentially create gravitational waves rippling through space. These waves will be incredibly weak by the time they reach us and will pose no danger to Earth, but they give us a new way to study the universe. Scientists have already begun to detect these waves with incredibly sensitive instruments, ushering in a new era of gravitational wave astronomy. Fortunately, the probability of a supernova exploding close enough to affect Earth is quite small, but understanding these potential dangers is crucial. It's a reminder of our connection to the cosmos and how events occurring light years away can have consequences right here on our home planet. As we've seen, supernova explosions are powerful events that can have far-reaching consequences. But did you ever guess that supernovae may have played a role in shaping Earth's history? Scientists have found evidence of past supernovae in the form of iron-60, a radioactive isotope in ancient geological layers and cores of Antarctic ice. Iron-60 is not naturally produced on Earth, but created by supernovae, suggesting that our planet was dotted with the remnants of these stellar explosions. One notable event is the Pleistocene supernova, which erupted about 2.7 million years ago. Some scientists speculate that this supernova may have affected Earth's climate during the Ice Age, perhaps even contributing to a period of cooling. There's also a theory that supernovae may be associated with mass extinctions. The idea is that cosmic rays from the nearest supernova could damage the ozone layer, resulting in increased ultraviolet radiation on the Earth's surface and harming life, especially shallow oceanic organisms. Although these theories are still being studied and debated, they highlight the potential impact of distant cosmic events on our home planet. It's a reminder that we're part of a dynamic and interconnected universe. As we look out into space, we're looking not only to the past, but also the future. Stars will continue to be born, live, and die, and some of them will end their lives as supernovae. But what does the future hold for supernovae in our Milky Way galaxy? Astronomers estimate that a supernova explosion in the Milky Way occurs on average about once every 50 years. However, most of these supernovae are not visible from Earth because dust and gas block the direct view. The last supernova visible to the naked eye in our galaxy was over 400 years ago, observed by the famous astronomer Johannes Kepler. But rest assured, astronomers are keeping a close eye on potential supernova candidates. These include such stars as Betelgeuse in the constellation Orion and Eta Keel in the constellation Keel. Both massive stars have unusual behavior, leading astronomers to speculate that they could become supernovae in the relatively near future on an astronomical timescale. A recent study has shed new light on the mysterious behavior of that celestial giant Betelgeuse. This star, known for its semi-regular variations, has been the subject of intense scientific scrutiny. In the context of a star such as Betelgeuse, these changes are visible in brightness or intensity of light. The star does not follow a strict cycle of increasing and decreasing brightness, but rather oscillates in a predictable but not entirely regular manner. Researchers have identified 4 different periods in the variations of Betelgeuse: 2, 200, 420, 230, and 185 days. They suggest these periods correspond to the pulsation patterns of the star, in particular the radial principal mode and the first, second, and third overtones. This pulsation analysis, which takes into account the complex interaction between pulsation and convection, suggests that Betelgeuse is in the late stage of core carbon combustion. The study also looks at the previously mentioned event known as the Great Dimming, which caused Betelgeuse's brightness to decrease significantly from December 2019 to February 2020. Researchers speculate that during this period, the effective temperature of Betelgeuse dropped by about 100 K, which may have resulted in significant mass ejection of the star. This event triggered a flurry of observations and analysis aimed at deciphering the secrets of this distant star. The researchers' findings lead to an exciting conclusion. Betelgeuse could be the next star in the galaxy to go supernova. Given the current stage of late-burning carbon in the core, its high luminosity, and complex variations, Betelgeuse is a prime candidate for participation in this exciting cosmic event. The study also notes that the star's high rotation rate as a red supergiant has sparked discussions about its evolution, including the possibility of past mergers with another star as a source of angular momentum. However, it is important to note that predicting exactly when a star will go supernova is extremely difficult because it depends on many factors that are not fully understood. Even if a star has indications that it might go supernova, it could be thousands or even millions of years before it actually goes supernova. But rest assured, when it does, it will be a grand spectacle. The study of supernovae is crucial to our understanding of the universe. These stellar cataclysms are not only endpoints, but also beginnings, saturating the cosmos with the elements necessary for new stars, planets, and possibly life. As we travel through the cosmos, we're constantly reminded of the grandeur and mystery of the universe. Supernovae are a testament to the life cycle of stars, the creation of elements, and the interconnectedness of the cosmos. We have studied their types, the dangers they pose, their impact on Earth's history, and what the future may hold. These celestial events, as destructive as they are also creators. They seed the universe with the elements necessary for new stars, planets, and possibly life. Studying supernovae is not only about understanding these spectacular events, but also about understanding our place in the universe. They remind us we are made of star stuff, that we are part of this vast, dynamic, and constantly evolving cosmos.